everyone, it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of this webinar, of this event this evening. Sorry. First, I will be reading the rules of the event. Second, there will be opening remarks by the chairman of ICE Jakarta Local Association, Phil Woodmansey. After that, the event will be guided by our moderator, Michael Dobby, and the event will then continue with a Q&A session. Ladies and gentlemen, for your convenience, please pay attention to the following rules. For the online attendees, you can submit your questions for the speaker to the Q&A feature located at the bottom of the screen. The question should be in English. You can raise your question before, during, and after the presentation of the speaker. For the on-site attendees, you can raise your questions later by raising your hands first at the Q&A session. Now, without further ado, I would like to invite the chairman of ICE Jakarta Local Association, Phil Woodmansey, to give his opening remarks. To Phil Woodmansey, the time is yours.
Thanks, Rifa, and welcome everyone. This will be our last event of this year. I'm pleased to say that we managed to get in about 7 presentations this year. And I also know that Mike and David have done some work presenting at Venus as well. So thanks to those guys. As you'll probably have noticed already, the company Multibangen have taken over the running of these events and the presentation. And I'm pleased to say that it's looking extremely professional. And I'd like to thank the team and Rifa, led by Rifa. So well done, guys. It's good to have you on board, and hopefully you'll be doing all that next year as well. So as we bring the year to a close, we are soon be setting the agenda for next year. So we're always looking for good quality speakers, one of which I'm sure you'll enjoy listening to tonight for sure. So if it's you or you know someone who may like to give a quality presentation next year, would be great to hear from you. And finally, as chairman of ICE locally, we are always looking for the next group of ICE members. You'll probably notice that those of us that are leading the institution now are in the later years of our lives, and there's a lot of gray hairs around, me included, and we are looking for people to step up and take over some of these roles. So that we have good succession in Jakarta, and we want to keep it going. So please give it some thought about becoming a member with us. So from there, I'll thank you all for joining tonight. I hope you have a good holiday over the Christmas period. And for the presentation, I shall allow Mike to step up and introduce our speaker. Thank you.
Thanks very much, Phil. And first of all, welcome to those who've arrived already. I think there may be a few more arriving, but today's is a very special presentation. For all civil engineers, an important element of what you learn in those early days should be the basics of geology, because geology forms our land. Whatever we're standing on is the result of geological processes. And certainly here in Indonesia, there are many processes going on, and some of them are very interesting. And I think that's what we're going to learn about today. So I'm hoping our students will arrive soon, because I'm pretty sure at Venus, they don't have a specific course on geology, which is a shame. But today will be a chance for them to learn about this extraordinary country and its geology. So let me introduce our speaker, Dr. Peter Woodroof. He's a geologist with extensive experience, 50 years of experience, which is quite something. In his earlier days, he graduated, he gained his PhD at the University of Oxford, which I'm sure you'll all realize is a very prestigious university in the UK, just to the west of London. And since those days, he's spent most of his years working in this part of the world. He has a lot of experience working here in Indonesia, although currently home is actually Malaysia, but because of a current job where he's working for Prima Energy. He's been mainly based here in Indonesia for the last 2 years or so now, I think. Yeah. So it's a great honor and pleasure, Peter, to have you talk to us tonight about geology. Please, of course, in Peter's field, he's working mainly deep in the earth. Our civil engineers are really only interested in the top 20 meters or so, but it all starts deeper down. So all civil engineers really do need to have a basic understanding of geology. It's absolutely vital because it's the starting point for everything that we stand on and everything we design later on. So I'm very much looking forward to hearing your talk tonight, Peter. Thank you very much for coming along so close to Christmas and preparing what I'm sure is a lot of material. So I would like to hand over to you. Thank you, Peter.
Thank you very much. Thank you. Anyway, good evening and welcome. And thank you to everybody for inviting me to talk. Right. I don't think there's much to say about this slide, so I will move on. This talk, if I can move on, that is, I'm not sure how do I operate this? There you go. Work this one. Yes, we're working. Thank you. So hang on to your seats. This is going to be a very rapid review of the geology of Indonesia. But also, I'm going to consider some of the geography and the history. While I'm a petroleum geologist or geoscientist, I'm still interested in all branches of geoscience. Let me start with an introductory slide. This is the first and only itinerary that you're going to see. Before I move into the tour proper, I'm going to introduce some geology to you. I think this is important because there's a lot of geology that I'm going to cover, so I will do that first. I will start in Sumatra, then I'm going into Java, then into Kalimantan before eventually ending up in Papua. I haven't been to all the places mentioned, but I visited a large number of them. I will end with some concepts that are well illustrated by Indonesia. So please excuse my bad pronunciation of Indonesian words. It would help perhaps if I can handle your questions at the end. If there's short questions, I can handle them going along, but there's a lot to get through. You may be familiar with geological tools. You may not. The clinometer was invented in 1880, and that measures dips. The digital camera, the geolocating camera, was invented in 2008 and is still only just coming into use. So when you take a picture, it tells you exactly where you are, where you're facing, very useful. For geology, we use contour maps, geological maps, and many other maps. The more maps, the better. We can never have enough maps. We measure sections on land, and we measure sections down boreholes for well logs. We use seismic lines, which is the energy pumped into the earth and recovered back. I haven't got time to tell you about seismic lines. If you want to know, I can tell you, but that will be a long session just on its own. And we make geological cross sections. These are important. We never make enough. And we also have to use Occam's razor a great deal to cut through the nonsense. But most important of all, we have to use science. This is something that is unfortunately not always being used. It is observations, experimentation, building knowledge by validating and falsifying ideas, but it must be testable and it must be able to be proven false. This last one seems to be lost. We have to be able to tell whether an idea is false or not. And there's so many false ideas still lying around that we haven't managed to get rid of. So science is never settled. Please don't rely on your feelings or don't rely on models. Models are useful for getting an idea or testing things, but they're not science, real science. Right. Naming of hills. This is a problem for Indonesia. Let me just tell you, the Dutch didn't learn any geology until the late 1800s. They sent Germans, they sent German explorers and German geologists. But unfortunately, many of the hills and mountains were not named. If the locals knew the names, they didn't manage to capture them. So if you see, the Dutch finally were able to make some maps and capture some names. But when the Indonesians took over, when the RBI took over, unfortunately, most of the names were not transferred. So most of the river names, this is a serious issue. There are many groups in Indonesia trying to rectify this because it's a cultural heritage that you've lost. So I find it hugely difficult when I go somewhere I don't know the names of the mountains. And in fact, I've had to invent some in the work that I'm doing. And of course, Google is awful. That has completely lost all real historical cultural names. So a problem, but I apologize where I've invented names, but that's a necessity. Okay, what are rocks? Three main types: igneous, sedimentary, metamorphic. Igneous rocks obviously include things from magma, such as granites, but lots of volcanic rocks are igneous as well. Scoria, pumice comes out of a lot of volcanoes here. And there's lots of sedimentary rocks. I'm sure you know your rocks: sandstones and shales and siltstones and conglomerates, those sort of things. But in Indonesia, there's a huge range of volcaniclastic rocks. These are rocks which are clastic, but they're made of volcanic material. So we call them volcaniclastic. Nearly all volcanic products in Indonesia form sedimentary rocks. They might be volcanic material, but they're actually forming sedimentary rocks. I'll come on to that later. Metamorphic rocks, also a number in Indonesia, but perhaps not so important. Right. Strata, sedimentary rocks are very important in Indonesia. We have all sorts of sedimentary rocks which form strata. Here are strata. All sorts of ages of sedimentary rocks in Indonesia. And most of the volcanic rocks, as I've said, are volcaniclastic. Most of the volcanic rocks are bedded. Therefore, it's important to understand sedimentation and stratigraphy. Just a bit of history here. I like my history. I never used to like history at school, but I like it now. 2,000 years ago, people were describing fossils. They didn't really know what they were, but they were describing. 500, but then 1,000 years ago in China, they realized in the mountains that these fossils must have been deposited in the sea and been somehow magically lifted up into the mountains. They didn't know how. But then good old Leonardo da Vinci started writing in the late 1400s. He described fossils in Tuscany, and he realized they were laid down by water, sometimes in the sea. And he realized as well that there were many floods involved. It was heresy to say there wasn't one single deluge, but he was one of the few people that got away with it. He didn't get killed or put in jail for saying there was more than one flood. So we owe a lot to Leonardo da Vinci. By the 1600s and 1700s, we started to talk about geological time. There was no agreement. We didn't know whether time started, whether it ended, whether it cycled. We didn't understand time in the 1600s and 1700s. James Hutton, who was the founder of modern geology, famously said, there is no vestige, no sign of a beginning, no prospect of an end. So he didn't know that there could have been a beginning, and he didn't know there could be an end. So that was probably the general feeling at that time. Since the last 60 years, we've accepted the Big Bang, and we have radiometric dating. So we now accept the Earth is 4.54 billion years old. However, we're still arguing about, I'm not going to go into all the latest on time, but it's quite interesting. Going back to rock strata, we now have, Leonardo da Vinci invented lithostratigraphy. He named different rocks in Tuscany by different names. and he called them lithostratigraphy. Relative age of rocks is relatively new, the last couple of 100 years, and it's called chronostratigraphy, time stratigraphy, time rock stratigraphy. Right. This is what some people come up with. This is a chart of rocks. It looks like a chart of time, but it's not. It's a chart of rocks. It's a chronostrat chart. But unfortunately, the International Commission of Stratigraphy mix geologic time up with rocks. Originally, we only knew that rocks were older or younger than each other, and we didn't know their age. Now we can date them, and we can actually fill in the gaps. So there's geologic time, which we assume is continuous, but there are rocks which are definitely not continuous. There's ages in here of which there's no rock deposition or rock records. So this system is what we use, but it has some disadvantages. The main disadvantage, which catches almost every student out, is that they don't know the difference between rocks and time. We call rocks systems theories of stage, and we call them upper and lower for obvious reasons. If you're out and looking at the rocks, if it's up there, it's upper. If it's down there, it's lower. But we call geologic time period, epoch, and age. And we use the term early and late, not surprising. Sounds very simple. You'd be surprised. Almost every geological publication I pick up mixes this up. It's a terrible mess. People don't know the difference between rocks and time, but I'm telling you, so you'll know what the difference between rocks and time are. If I say Upper Cretaceous, I mean rocks. If I say Late Cretaceous, I mean time. It's as simple as that, but most people get it wrong. Now, what happens in Indonesia is we're more interested in the last 60 to 50 million years approximately. We're not really, there are plenty of older rocks, but we're really interested in the last 50 million years because a lot has happened. And the good old ICS has got rid of the tertiary, but the tertiary is still alive and well in Indonesia. We still use it and we still recognize it because it's so important. They've done away with the tertiary and called it Paleogene and Neogene. But you can use those names if you want, but probably tertiary is still very much in use. So you'll maybe hear me say tertiary, even though it's apparently doesn't exist anymore. Did I? Right, let's move on. Let's go to Indonesia and its place in the world. Fascinating subject. You'll notice that Indonesia often gets badly treated. And this is an example. This is an absolutely typical tectonic plate map. It shows Indonesian islands missing. It shows an incorrect boundary between what's called the Australian plate and what's called the Eurasian plate. It even shows a plate boundary that doesn't exist yet between the Indian plate and the Australian plate. I could go on and on and on. But suffice it to say, the people that make these maps are not located here. This is a beautiful map. This is made by the National Oceanic and Aeronautic and Atmospheric Administration, NOAA. Lovely map. And what I really want to point out is that, okay, to the south of Indonesia here, Indonesia is centered on this map of the globe. The Indian Ocean here, the Wharton Basin is 7.5 kilometers down. I'm using metric system and I'm using meters and kilometers. Internally here, within the band of sea, there is also a deep area that's over 7 kilometers down. And for those of you who have been to, I'm going to say Irian Jaya without apology, if you've been to Irian Jaya, then you'll know you can go up nearly 5 kilometers, Puncak Jaya. So here you've got about 12 kilometers of relief. This is a relief map. That's the only word there is for both bathymetry and topography combined. We don't have a word for bathymetry and topography combined, but relief is the only word that we can use. So here, up against, say, for example, some of the highest mountains in Java, you have, again, over 11 kilometers, nearly 12 kilometers of relief. So it's quite a substantial relief within a few hundred kilometers. And there's good reasons for that, which I'm going to come on to. The plate tectonic structure of Indonesia. looking at you'll see somewhere called Sunderland. This is a geologic term, although it might be a cultural term as well. This area has come together with lots of different bits, but it's been assembled before the Cretaceous. The Cretaceous is anything really before 66 million years ago. And it includes a large part of Sumatra, all of Western Borneo, and then you have another piece here called the East Java terrain, and I'll come on to terrains in a minute, which attached during the Cretaceous, maybe 100 million years ago, and is now reasonably attached. Not totally. This is totally attached and really doesn't move. This does occasionally move, as we'll come on to. And then you've got the rest of Indonesia, most of central and eastern Indonesia, which is very much on the move. It is still assembling. We don't even know which direction some of it's going in. And I'll come on to the various bits in this area, which are absolutely fascinating. The Australian plate's here, but probably finishes here. West Papua, or let's call it the western side. This bit is called West Papua. This bit's Papua. This bit's West Papua. This is hybrid between Australia. It's Australian up until maybe the Cretaceous, and then it becomes part of Southeast Asia. So this is a hybrid area, which is really West Papua. There's been a lot of development here. I haven't got time to tell you all about it, but pretty solid, less solid, moving around. That's probably the best way to summarize it. Okay, what's happened? Well, lots of oceanic plate, the oceanic lithosphere. There's in the ocean, it starts out very thin at the ridge crest, wherever it's made. And then as it moves away from the ridge crest, it gets thicker and thicker as it solidifies up to about 100 kilometers thick. And it subducts underneath at things called subduction zones, which I'm going to tell you quickly what they're all about. And this example, thanks to Pabelier in 2005, he put together, you can see that in the last 15 million years, up to 1,000 kilometers of oceanic lithosphere has subducted under Indonesia. It's gone down and it's gone underneath Indonesia. And I'll show you in a minute where it's gone. Okay, this is subducted ocean and plates have moved around. You can also see there's quite a lot of movement of oceanic plates here. I'll show you some examples up here where plates have oceanic plates, that's oceanic lithosphere, has moved around and subducted. So there's subduction zones all around. Indonesia's a good place to study subduction zones. But it isn't in the Pacific Ring of Fire. Honestly, it is not. Indonesia is its own arc. You've got to stand up. It's not anything to do with the Pacific. It's everything to do with the Indian Ocean and Australia and Eurasia. And you have an Indonesian arc of fire. You don't have the Pacific Ring of Fire. The museums are all wrong. I'm sorry, but even some of your ministers get it wrong. So I'm been told. Okay, what is it? It's the Indonesian Arc of Fire. It's an important volcanic arc, one of the most important volcanic arcs in the world, worthy of lots of study, worthy of its own name. Okay, it runs from Sumatra down all the way to Alor here, then it takes a kink through the Banda Arc and up into the Malacca Seas. It's a good arc. It's not a ring, it's an arc. It's the Indonesian Arc of Fire. I will tell you more about this because one of my hobbies is studying all the volcanoes, all the quaternary volcanoes of Indonesia. Right, what is subduction? Subduction is oceanic lithosphere, which includes a crust, which gets thick, gets heavy, and it decides to go down underneath whatever, underneath another plate, which is normally a continental plate. And it goes down. And it forms a subduction channel. There's been lots of work on subduction channels now, but we don't obviously know much about them. But it's the most important part of the subduction because not only do rocks and sediment go down, but water goes down as well, goes down to about 120 kilometers down, Water then comes up along with other fluids and when you add water to rocks, it significantly lowers the melting point. So if you put hot water into the upper part of the rocks overlying a subduction zone, you get melting. That's where your magma comes from. This is nothing to do with Hawaii, Iceland, or any of those lovely pictures you see of flowing lava that you see on all the documentaries. The documentaries are wrong when it comes to Indonesia, okay? This is what happens. The water lowers the melting point and you get magma. And you get very interesting magma. Okay. You get water-filled sediments. Even the lithosphere has a lot of water in it. The rocks dehydrate, and at about 120 kilometers down, the hot fluid, which is mainly water, rises up. You can get thin lithosphere, which will subduct or even obduct, but I'll leave that out for the moment because that's going too far. Now, this massive circulation system is so important geologically. It's responsible for creating large volumes of granitic magma, which are called batholiths, and they're plutons. I probably haven't got time to show you. I'll show you some examples. And it's what creates most of the mineralization. This water, millions of years, is rising up through here, and it's creating mineralization. So most of your minerals are being generated here over millions of years. And of course, you get earthquakes. So a subduction zone has a lot going on for it geologically. What's an Indonesian subduction volcano? Well, it's andesitic rock. It's high in silica and sodium and potassium and a few other things, but it's viscous. It won't flow. You don't find Indonesian lava flows. They don't exist. They do. I'm lying. There's a couple I walked up. There's one at Lukon in North Sulawesi we walked up. Very, very rare. The lava, the magma rarely gets out of the volcano, and it forms what are called lava domes. Indonesia has thousands of lava domes. These are very important. The lava blocks up inside the volcano. The lava grows from the bottom, pushes out until eventually it either collapses or explodes. When it explodes, then obviously you get lots of rocks, lots of ash, everything comes out, including lots of water and CO2, the volatiles which are coming up from deeper. And what happens is you oversteepen. You continually collapse a volcano. I've been looking at all the volcanoes of Indonesia, and you can see how they develop. It's probably one of the best places to look at this type of volcano. And there's lots of calderas. I'll show you some of them. There's more than 50 calderas in Indonesia, probably closer to 100. It depends how you count them. But that's because the magma chambers are relatively shallow, and when the magma moves, then you get collapse of the ground. That's a main method of forming a caldera. Now, we've also got earthquakes, as I said. Most of the earthquakes are shallow earthquakes. This is red, is less than 100 kilometers down, and it is related to the movement of the plate pushing the other plate, pushing the accretion, what it forms an accretionary wedge. It's forming sediments which are thrusting here and forming earthquakes. So most of those earthquakes are a result of thrust faults, which I'll show you in just a minute. You can see sometimes you get deep earthquakes. That's where you get the oceanic lithosphere subsiding into the mantle, but it's still got enough brittleness to be able to form to crack and form an earthquake. So the subducting oceanic lithosphere doesn't melt. It is still pretty solid when it reaches 600 or 700 kilometers down. And you can see there's this area in here particularly, and also the area west of Malacca, that west of Sangihe. Very interesting. This map also shows you this line here is the Flores Wetar back thrust. And I'll show you about that in just a minute, because it's a very important back thrust that you need to be aware of. So what happens in subduction? This now we know through listening to earthquakes. We can record earthquakes and we can image the deep earth by an earthquake. And that's what tomography is. So what happens is this is an interpretation of what's happened underneath Indonesia from the Australian, Indo-Australian plate subsiding. We can see that typically it will sink to about 660, which is called the transition zone. It'll stay there for a while. It might move laterally before it changes phase, becomes more dense, and then drops into the lower mantle. That's very important because when it drops into the lower mantle, it not only creates tectonism, faults and folds and things above, but it also allows the subduction to move. The subduction zones move laterally. When they start blocking, they start moving that way because they can't move that way. But when you avalanche the slab into the mantle, it can then suddenly retreat back. So the position of, and I'll show you, the position of subduction zones changes over time. What's a geological terrain? I've mentioned that. Geological terrains are basically bits of lithosphere which come together, which usually have been brought together by plate tectonics where subduction has occurred, the oceanic crust has disappeared, and they come together. We get lots of what's called accreted terrains in this example, where the subducting slab pushes different bits and creates faults and pushes different bits together. So we can see over time, there are lots and lots of terrains. Here are some of the terrains of Indonesia. Not all of them, but some of them. This is the Sundaland area. You can see already that Sumatra is divided into several terrains. It has Sibumasu, it has the East Malaya terrain coming down, has a West Sumatra block, the Woyla terrain. It has the Southwest Borneo, what I just showed you before, the East Java terrain, which is really this piece, and a whole series of terrains over here. Now, Western Irian Jaya, which I know very, very well, I've spent 30 years working Western Irian Jaya, and I can tell you there are more than one terrain in Western Irian Jaya. So we can see it's very complicated here. Here the terrains have come together, and that's what we call Sundaland. The rest of it is still moving around. Okay, faults, just quickly, I'm sure you know faults, but if you didn't, I'm explaining them to you. They're typically, a single fault is usually not more than 20 kilometers or 2 kilometers in throw. They can be a bit longer, but not often. If they're longer, they're normally fault zones. There are a whole series of faults which don't necessarily join together, but form a swarm of faults. And they can be normal faults, strike slip faults, which are particularly important in Indonesia, and reverse faults. And when they're low angle, they're called a thrust. And you can see the fault blocks that form are things like horse and grabens. You can get half grabens forming. And there's things called curving faults, which we call listric. That's all listric means. It just means curving. And if you get a curving fault while the sediments are still being deposited, you get what's called a growth fault. We like growth faults because they're a great place to trap oil and gas. And typically, listric faults go out on a decollement surface. Somewhere in the subsurface, there's usually a level that is mobile. There's usually a shale there or something down there that will cause decollement. And decollement's very important for fold belts. Here in Indonesia, I was going to try and find time to tell you how many fold belts there are, but there's actually a lot, and I'll show you some. Fold belts are where usually they form where there's some convergence, and you usually get decollement. Sometimes you get gravity slumping, and often lots of thrusting. So there's all different sorts. You can have everything from just folds to almost entirely faults, but in which case they'd be called a fold thrust belt. So there's a whole range of fold belts. I haven't got time to show you all the variety and names of fold belts. Now, this is important for Indonesia. Many of my students get this wrong. Inversion is a particular name given to uplift of an area that has deposits in. So if you have a half graben full of deposits, and then suddenly the stress regime changes and maybe the fault change, you get what's called inversion. You can even, when the basement or the lower levels come back up more, then it's called total inversion. This happens all over Indonesia. I'll show you some examples. It's very important. We never know in the oil business whether we like them or not. If they're too young, they haven't got any oil in. If they're old, then they're usually okay. But if it's uplifted too much, the reservoir is completely lost. So we don't always know what to do with an inversion. But this is something that's very common and very important. When we say inversion, it doesn't mean just uplift. It means uplift of an old, low, thick sedimentary area. Here's an example. This one's in West Natuna, and we've actually named them. We call them Sunder Folds. You can see here, here's the half graben with sediment, and it's been uplifted a bit. This one's uplifted more, and this one's completely squeezed out and uplifted. This is typical of what you see in many parts of Indonesia, in South Sumatra, in even over in East Java. A whole range of different areas have inversion. It's a very important process. It usually happens because over time, faults will change the orientation that they're moving. Right, we're moving on to Indonesian history. And because it wasn't taught in the Netherlands until just over 100 years ago. And to do a geologic survey, you need good maps. You particularly need good topographic maps. That's why William Smith was able to run around England and make maps very quickly, because he'd been given the latest topographic maps. I shouldn't demean William Smith, but that's what he did. And in Indonesia, the first surveys, really the first geological studies started in the 1840s and not really until late 1800s. And it was almost all by Germans. The Dutch sent Germans out, or they allowed Germans to come out here. In fact, many of your mountains and other things are named after Germans. They're not named after Dutchmen. Okay. Its mapping didn't actually start to 1905. And then the Dutch started to learn geology, and they had some wonderful geologists. So over the years, the 40, 50 years of this mapping, the Dutch were able to send several good geologists out. And then as a parting shot after the war, Van Bemmelen published The Geology of Indonesia. I'll tell you a bit more about this because he's a very interesting gentleman. He actually stayed here during the war. And then obviously there was a long period where very little happened due to depression, war, independence, etc. And the first work in Indonesian language was published in 1962. And then in what was still Netherlands, New Guinea, Visser and Hermes, I call it Irian Jaya, but Visser and Hermes published a very nice, good work in English. These were Dutch gentlemen in 1962. Since 1970, we've seen a significant growth of Indonesian geology. We see lots of universities teaching geology now. I can't even tell you how many universities in Indonesia. There's probably more universities in Indonesia teaching geology than in the whole of Europe. That's how significant it is. Obviously, if you live in a country with lots of rocks, lots of hills, you're going to learn and want to know about geology. Okay. However, there was a German that came here in the late 1600s, and he lived in Ambon, and he described rocks. I'd only just call him a geologist. He mainly described plants, but he lived in Ambon and wrote lots of things. And his name was George Rumphius. Then we had a brief interlude, as you probably know, 1811 to 1816. So Raffles came over, decided to tour around Java, and he wrote quite an interesting book. I read it, actually read it the other day. It's a nice book, mainly describing the people and the culture, but he also described the landscape. So there's some useful things, and he supported studies. He presumably thought that from 1811 on, that he was going to be in charge of Indonesia, but he was forced in 1816 to give it back to the Dutch, so he didn't get a chance to stay. Then, sort of a German naturalist. I'm never quite sure when a naturalist geologists or not, but anyway, he went to Kalimantan, this gentleman, Salomon Muller, and he went to Kalimantan, walked all over Kalimantan, and wrote a book on his travels. And the Muller Mountains are still one of the few named mountains in Kalimantan. There aren't many named mountains in Kalimantan, but Muller Mountains are one of them. This gentleman is actually one of the most interesting. He was an eccentric German. He ran away and decided to live in Java. He traveled all over Java and he loved to draw. And here's a picture of him. I don't know how he managed to get himself in, but anyway, he did have a camera later on, but this is obviously a drawing. This is Merapi here, and this is to the north is Merbabu. I'll show you where that is if you don't know. This is also very interesting. This is Lamongan, Gunung Lamongan. But this, he painted it from what's called a maar. This is the Ranu Klakut maar. This maar is a volcanic crater without ash. It's just hot water that erupts and forms a crater. But because there's very little or no ash coming out, it doesn't form a edifice. It doesn't form a cone. So this is a maar. And if you look around Lamongan, if you go here, there's about 50 to 100 maars. It's a fascinating area of East Java. He also was worried about getting malaria, so he allowed the development of these, he forced the development of cinchona trees, the fever tree, which was quinine. So he wanted people to take quinine to stop them getting malaria. And that's where he died in fact, he died in Lembang near Bandung, and there's various memorials to him in Bandung because he died there and said, I love the place. Verbeek was probably the first real geologist. He was living in Bogor when Krakatoa erupted in 1883. So he obviously decided to better go out and have a look. And obviously this is something that Mike knows very well from the other side. You don't see this side, do you? This is Rakata, which is the part of the original Krakatoa. And this was his drawing of it erupting. So I don't know what else he did, but he obviously decided to go to have a look at Krakatoa. Probably the most impressive Dutch geologist that we know about is Louis Rutten. He joined an oil company and he worked all over the place looking for oil. And then in 1927, he published a really good book. You can see it's not in English. It's his lectures on geology of Indonesia. And it's wonderful. He did very good cross sections and we have a lot of respect for him. To conclude, the Dutch Van Bemmelen was asked by the Dutch government to summarize everything that had been done. They suddenly woke up, I presume, and decided that they'd better find out what minerals and what rocks there were in Indonesia. So they asked Van Bemmelen, who was here, and he stayed here all through the war. He got on well with the Japanese, and they allowed, because I don't know if you know your history, but obviously we still to this day don't know what Dutch did during the Second World War. They were allegedly neutral, but that put the Japanese in a very difficult position when they came here. They didn't know what to do with the Dutch. Some were killed, some decided that they were going to be happily working with the Japanese. And Van Bemmelen was one example, and you can just read his preface here to the excuses or the comment he's making in the front page of his book. But it's a very good summary of the geology of Indonesia. Published obviously when he'd actually left Indonesia, and that really is the last parting shot of Dutch geology in Indonesia, apart from Netherlands, New Guinea. We now have some great Indonesian geologists. Probably the most famous is John Catilli. He was born in Gorontalo, which has got to be a great place to be born if you want to be a geologist. He got the first doctorate from ITB. And he wrote for schools. He wrote this book. It was called Overview of 3 Billion Years of Earth History. I haven't read it, but it's a book he wrote for the schools, and they gave him an award, the Bintang Mahaputra Adi Pradana. I don't exactly know what that is, but it sounds impressive. There's some others. A mining man here was well known. There's a book to him, and we're pleased to still have Raden with us, and he still occasionally gives talks. He is the father of Indonesian oil and gas geology. And he went to Colorado School of Mines, which, if you don't know, is perhaps one of the premier geological schools in USA. Okay, and here is a map. Herman Darman gave me this map the other day, his latest version. Herman is a great example of a young Indonesian geologist doing great work. And he does lots of initiatives, and one of them was to make this simplified map of the geology of Indonesia. I can use it. You can basically see what's of interest. Paleozoic means old. Paleozoic rocks of sort of 300, 400, 500 million years old. So they're very old rocks. Look where they are. They're over here in Sumatra, and some are in Papua and West Papua. And Mesozoic rocks, there's a number of Mesozoic rocks in a very difficult place to get to here, and quite a few in West Papua. I'll tell you about that in a bit more. So that's a simplified but useful map, thanks to Herman. I'm now starting your tour. Okay. Sumatra, I've laid it on its side. Once upon a time, it was this orientation before it smashed into Sunderland. I'd like to just summarize for you, because these relief maps are very useful. Where you see white, that's over 3,000 meters high. So it's very significant when you see white. And that's where Kerinci this is the backbone of Sumatra. This is the Barisan Mountains. It's mainly volcanic. And Kerinci is the highest volcano in the whole of Indonesia. And there's a whole range here. But what really isn't Barisan Mountains is you've got this huge lump here called the Toba Plateau, and you've got this head, which is the Aceh Highlands, which has lots of old rocks in it. There's a lot of old rocks in here and not that many volcanoes. And I'll come on to that. That's a volcano, but Lhasa isn't. This is a hard place to get to. I've never climbed up Lhasa, and I don't think I ever will. Some of you might have done. I'm quickly going to show you a couple of other things, Bangka and Sukadana, because Sukadana is interesting. This is a right way up map. North is up of Sumatra geology. You can see in blue, this is Mesozoic rocks of what's called the Woyla terrain. Here, Woyla terrain. This is a part of Sumatra which docked some time ago. So, but it is now part of Sunderland, but it's a separate part. And there are lots of Upper Paleozoic rocks. Particular Upper Paleozoic is the name for rocks. They're not. I could say rocks deposited in the late Paleozoic, but I'm going to tell you Upper Paleozoic. So if I say Upper Paleozoic, that means I'm talking about rocks. Okay. Lots of interesting rocks, somewhat similar to the rocks you see in Peninsular Malaysia, where I spent a lot of time looking. And there's Mesozoic granites, and there are granites over here in what's called the Tin Islands. So there's a big fault made up of a whole series of smaller faults called the Sumatra Fault. Some people call it the Great Sumatra Fault. It has a few other names. But everywhere you'll see this fault is made up of a lot of fault segments shown in red and blue. And it's dextral, it's right lateral, okay? It's being forced this way on this side by the moving Australia plate. Now, you'll see some of the movements. You can see it's typically a couple of centimeters per year, whereas if you look at the movement of the Australian plate, that's typically nearer 6 centimeters per year. So this is about a third. This moves about a third of the speed of the plate here. So about a third of this is translated into movement in this direction. Interesting fault. It's still active. You can see the fault trace, which is quite nice. You can actually spit like the San Andreas. You can go and see ups and downs and the fault trace on the surface. Right, Toba Plateau, misunderstood. This is thanks to Van Bemmelen, some of his writings. It's a big uplift. It's not a stratovolcano. It's not a large volcano. It is an uplift of Paleozoic rocks with what's interpreted to be Triassic granites beneath. I don't know if they're all there, but let's assume he's right. The only volcanic sediments are in purple. So basically, there's a thin skin of volcanics. There's a couple of small volcanoes like Pusa Bukit. If you've been to western side of Toba, here's Samosir, and there's some small volcanoes around. Not many. There's a probably 10 plus small volcanoes around Lake Toba. It's a plateau and it's a high area because of uplift, which I'll tell you about following, but it is famous because it's calderas. It has erupted material from various calderas, which are now covered by water in the most part, not all of them, but mostly covered. It's very interesting. There's circular calderas, there's rift calderas, there's a whole sequence of calderas in here, but basically it's a huge uplift of upper Paleozoic rock, of Paleozoic rock. What do we think caused it? Well, the most obvious reason for the uplift of Toba is it's had the investigator fracture zone going down it. If you travel Garuda, they don't know where that is. They put it over here somewhere, but that's their problem. I hope the pilots know where they're flying. But this is the investigator fracture zone. It comes into the middle of Sumatra. It subducts, and it's a whole series of ridges. So it's sticking proud of the general ocean floor here, which, as you remember, gets down fairly deep here to 5 kilometers or more here. But here it's not so deep, and it has, I'm not sure of the amount of relief on this, but let's say there's a kilometer or two, and it's gone down, and we believe that's responsible for buoying up and pushing up Lake Toba area, the Toba Plateau. And as an example, we can see around the world where seamounts and other ridges go underneath subduction zones. They even leave scars in the overlying rocks. It's very interesting now we can start to see this around the world. Okay, Sukadana basalts. Now, this is nothing to do with subduction. We know around East Asia in particular that there are hotspots that are what we call deep plumes, which rise up from depth. And this is one. This is the satellite image of Sukadanas here. But if you look carefully, you can actually see the edge of the basalts, and you can see a number of cones and buildups of lava. This is real lava. This is as good as anything in Hawaii. It's actually got lava tubes. So the lava is not viscous. This lava flows. As soon as it comes out, it comes up within days from very deep down. Then it flows out in a flood of lava and forms little cones, which can form in a matter of 1 or 2 days. And then it's all gone. You have to be quick to see this. So this is a map of those basalts. I won't go into all the details here, but this is where it is. It's in East Lampung. I don't know of any other example in Indonesia. This is fascinating because it's liquid, very non-viscous basaltic lava, which hasn't mixed with any rocks on its way up. It's come from very deep. In other parts, you'd find rubies in this sort of rock, okay? But I don't know of any rubies in this, but I haven't gone looking for them. And it's also important because, well, I'm going to tell you about diamonds as well. Okay, but before that, I'm going to tell you about tin mineralization. Tin forms in and around granites, a particular age, and these are late Triassic, and we can see all up through into Thailand, you get tin. All around KL, you'll see old tin mines. The mines are mining the sediment which has come off of the granite. So as the granite weathers, the tin comes out and the granite stays in the sediment. And we have an example here of Bangka, where you've got significant quantities of tin, but I believe they've stopped tin mining now. But they're lucky because they've also got rare earths and uranium. And it's just been announced you're going to have your first nuclear power reactor here. So at long last, I'm very pleased to say you're going to have a nuclear power station. The South Koreans are going to build it and send it over. That's fantastic news. I'm a great supporter of nuclear power, even though I'm a petroleum geologist. Moving on to Java scale. Java, I've kind of missed Krakatoa off because you can read about Krakatoa anywhere. But Java has calderas on the west, has the Ranau Danau caldera, nice little caldera on the west here, and it has the Sempol or Ijen caldera on the east. So it's got several calderas, but both ends have got calderas. It has uninspired named mountains. They're called the Southern Mountains. I wish they could come up with it. I haven't named them myself, but these are called the Southern Mountains, the west side, and this is called the Southern Mountains, the east side. So please name them if you can. I'll tell you more about them in just a minute. The Dieng Plateau is also fascinating, and here you can see some of the mountains. This was the picture by Jung Hung. He was standing on Merbabo and painting a picture of Merapi, and this is Lamongan here. This area is full of Mars. If you go and have a look at this area of East Java, you'll see it's lots and lots of craters all around, which are fascinating, and that was the one here that he took, not took the picture, drew the picture. I'm going to show you the Simandiri fault. You can see this fault. You don't need to be a genius to see this one. This is probably the most important fault in Java. That's Earthquake Alley. This is the Rembang fault zone that runs along here. I'll show you both those quickly. Okay, this is a very simple geology map, thanks to Van Bermelen, apparently 1970, must have been just before. Anyway, these are old volcanics. These are mid-tertiary volcanics in blue. Here's the Southern Mountains. And that was when the subduction zone was further south. The subduction zone is now here, but when these volcanoes formed, the subduction zone was further south. Oceanic lithosphere has gone up. It's probably avalanched down, and the subduction zone has moved back north. So subduction zones move around, and as a result, the volcanoes move as well. Volcanoes are very well regulated. They like getting their water from about 120 kilometers down, and that tends to happen roughly the same place everywhere. That's why you get this linear range of volcanoes, quaternary volcanoes. This area is interesting. I'm going to show you that. That's the Rembang Madura anticlinorium. It's an inversion zone, as you might guess. Very important. Well, I'll show you on the next slide. On the next one after this. This is the Simandiri fault. And I was sat on the 53rd floor of my office here on the midday, 2 o'clock, I think it was, 21st of November, 2022. And I started moving all around because this is a strike slip fault. It's a left lateral strike slip fault, the opposite direction to the Sumatra fault. And the fault, unfortunately, devastated Cianjur, including my father-in-law's house. I didn't know at the time of the earthquake, but we found out later. So you can see a huge amount of these shallow strike slip faults are incredibly dangerous. They can do a great deal of damage. This one is particularly obvious. This is being pushed north. The Southern Mountains are being pushed north and moving along here. Doesn't quite reach Bandung, but very nearly. This is a dangerous fault. This is Earthquake Alley. So if you have a choice, best not to try to live there. Moving to East Java, and we have the Rembang Madura zone. Here's a map of that. Here's Madura, here's the Rembang faulting. This forms a whole series of inversions, but it also forms a whole series of mud volcanoes. This is a map showing in red mud volcanoes, and just last week, Bledug, I like that name, Bledug Anak Kasongo erupted. This is a picture from last week. That's how recent it is, and that's here, and the old Kasongo is visible here. So there's a whole series of mud volcanoes. There's a famous one, Lucy, which of course you've probably all had lectures on, is a self-induced mud volcano, but nonetheless it's in that trend. I would go as far as to suggest that some of the Madura Straits is a result of some of this mud volcanism where the mud gets washed away. So this is a very shallow area of inundation. Probably eventually Madura Strait will move inland a bit more, which is a shame because we've got a house here, but never mind. Moving on to Kalimantan. Okay, Kalimantan, what a difficult, complicated island it is. Not probably the most complicated, but it is pretty difficult to understand. Here's the Schwanner Mountains. I can't tell you anything about Mr. Schwanner, other than he was German, but he walked from here across to here, and he decided to name the mountains. These are the Muller Mountains here. Finding the names of these mountains is very difficult. I've named them, but I'm willing to be corrected if somebody knows the correct names of these mountains. You can see very interesting mountain range here called the Meritus Mountain. That's an Indonesian name. Meritus is a local tribe. This is a part of the East Java terrain called the Paternoster Platform. Mahakam Delta is a world-class fluvial tidal delta. Very interesting. If you ever get a chance to go there, very interesting. And this is the Mangkaliat Peninsula. Again, actually, I haven't been there. We're planning to go here because this is a fascinating area as well. And we know a bit about this area because of the oil exploration in what's called East Cal. Let's move on while we've still got time. I'm just quickly going to take you up here. I'm just going to take you up here into what is part of Indonesia. The whole of the Natuna area, thanks to Natuna Island, is Indonesian. And there's lots of oil and gas in both East Natuna and West Natuna. This is fascinating. This is the Natuna Alpha structure, Natuna D Alpha structure. It was a gas discovery from 1973. It's a huge gas discovery. You can see it's a big reef will build up. And the problem with it is in this area of Malaysia, the West Laconia area, there's lots of deeply buried limestones. And if you bury limestones deeply, if you heat them up to 200 degrees centigrade or more, they start churning out huge quantities of CO2. Limestones are a repository of CO2, but you heat them up and the CO2 comes off. So what's happened is huge amounts of CO2 have come out of the West Laconia area into this reef, and therefore 71% of the gas in here is CO2, and nobody's yet decided how to develop this. I put it in because every now and again you'll see some mention of it when somebody comes up with a new reason as to what they think they can do. I think I know, but I'm not going to tell you because it would be politically incorrect. Okay, the geology, you can see. This is Sunderland. This is the Schwanner Mountains, which I'll show you a bit more of because it's quite interesting. You can see the mid-ranges. They didn't know what to call them. They called them the Central Borneo Ranges. That's how boring it is. There's no proper mountain names here at all. But we have got the Muller Mountains and the Schwanner Mountains and the Meritus Mountains. That's about the only named mountain ranges that are any confidence on. Okay. This is the boundary here between the East Java terrain and the rest of Sunderland, or this area of Western Kalimantan. And I'll come on to those because they're very interesting. Schwanner Mountains are an example of a big batholith. So this is thought to be late Cretaceous in age. The batholith underlies here, and these are all plutons sticking out of what is metamorphic rock. in blue here is metamorphic rock. Okay, I don't know much about this. This metamorphic rock has been dated at various times, so I don't really know what age it is. But this is a huge batholithic area, not unlike what you see in Peninsular Malaysia, very similar. So easy to believe that this is part of Sunderland. Okay, ladies. Okay, we have Kalimantan, and Indonesia has the oldest, one of the best sources of fine diamonds in the world. How many people knew that? Put your hands up if you knew it. One. Two people knew that. Isn't that sad? I'm sorry, but it's sad. You have some of the best diamond mines in the world, and most people don't even know it. So these are just some examples. If you want to see more, you can check with my wife. She might have a few on her. Most of them are found in this area here, the Chempaka and Seran swamps. Here's Banjarmasin. This is the Meritus Mountains. Okay, I have a very close friend who's an expert on diamonds, and we talk about this. He's not sure where the diamonds come from. However, you've got very old, interesting rocks in the Meritus Mountains. You have some peridotitic breccias. Peridotite is rock from very deep down. And peridotite can contain some diamonds. And these rocks in the Meritus Mountains, I think there's a handful of diamonds been found. So some people think that this is the source because the rivers all come from it, of the diamonds in here. Others think that diamonds survive a long time. As long as they come up quickly, they've got to come from a few hundred kilometers down up to the surface in a matter of 2 or 3 days. If they take longer than 2 or 3 days to come up, then they tend to degrade to graphite. But once they reach the surface, they become very stable, and that's why they're prized and they're very nice. They've dug down in the swamps here into what are fluvial sediments beneath, and they've found quite a lot of diamonds. There's a lot, and they've even got diamond cutting here. So they've got diamond cutting, diamond grading, everything you ever want from diamonds comes from this area here. Absolutely fascinating, beautiful diamonds because they have some wonderful colors, greens. We particularly like the cognac color, which browns, and even blue. So there's some wonderful diamonds, and you have one of the world's biggest diamonds. The Trisakti diamond was 166 carats, but it's gone missing. We don't know where it is. And if you read Raffles, he even tells you they found a 360 carat uncut diamond. So there's a lot of very good diamonds come from South Kalimantan. But don't tell anybody. Okay, moving to Bali and Lombok. Bali, you all know, you've all been there, so you all know about Bali. You can see Batu Caldera and you can see Mount Agung and everything. I'm not going to tell you about that. More interesting is Lombok, Rinjani, and the area near to Rinjani, the Samalas Caldera. The reason I'm going to tell you about that is this is the biggest recorded eruption in Indonesia's history. Standasad Tambora. This is possibly twice as big. We now know it's recorded. So it was written records in the Babad, Lombok. And we now know that there was a city called Pamertan, and I suspect it was about here somewhere, but I'm not certain. This was 4,200 feet high, and all this area came out in a very short space of time and formed what can be called a caldera. It's a crater really, but it's a caldera as well. It's big enough, if a crater is big enough, you can call it a caldera. And this put out a huge amount of ash and pumice. These big explosions put out pumice. Pumice is interesting because if it gets into the water, it floats. So you can often see after a big volcano, you'll find the sea is full of pumice. Pumice floats. Okay, how are we doing? Okay, we're getting on. Look, we're getting far east now, so we're getting there. This is Sulawesi. We've got two K-shaped, two funny Ks in islands. We've got Sulawesi, and we've got Halmahera. And they are probably this shape for the same reason. They are, and I'll show you the reasons. I struggle again with the mountain names. I can't really tell you for certain whether this is correct or not. While I'm on this, okay, there's two very interesting volcanoes on Sulawesi, which shouldn't be where they are. The main volcanoes are here, up in North Sulawesi, but there's Una sits in the middle of Gorontalo Bay, and there's Lompo Batang sits down here in the very south. I'm still puzzling over these and what they mean. I don't have the answer, but they're interesting. Most of the volcanoes are subduction volcanoes up here. There must have been some subduction that caused this, and perhaps this as well. Lots of islands I've never been to, probably never will go to. Buru, you may know, is famous because Suharto had it as a prison camp. I believe that was correct. Yes, thank you. Okay, Seram, I'm not really going to deal with. This is Raja Ampat over here, you can see, and I'm going to tell you all about the Malacca Sea in just a minute. Okay, the geology. So this western side is really part of Sunderland, whereas the rest of it is a result of lots of extension. There's lots of spreading here, and lots of movement on left lateral faults. There's some huge faults. As you know, the Palau fault gave a very big, devastating earthquake a few years ago. All of these faults are moving, and you've got lots of what are both ophiolites and old rocks. I will tell you a little bit about ophiolites, but there really isn't time to give you a full lecture. But suffice this to say, these are pieces of oceanic crust thrust up, as well as deeper rocks, which become exposed. What I'm going to show you is up here, the Molino metamorphic core complex, because that's interesting, and I'll show you a couple of other things. I'll show you Buton Island down here. This is the Molino metamorphic core complex. I've put this cross section on its side so you can see this area. Although Gorontalo Bay is spreading and is collapsed and is very deep, this area has been uplifted, and it's uplifted this metamorphic area here, very old rocks from some fairly low down, and the overlying rocks have slumped off. You can see here, it's come up and these rocks have slumped down. So these rocks have slumped off, exposing this core complex. I don't know where John Cotilly was born, but somewhere near here. Perhaps he did some field work on here, but this has become a very good example of what's called a core complex. It's the rock from deep is pushed up and the overlying rocks slump off the side, exposing very old rocks in the middle. Very interesting. And what I really want to come up with is, or what I want to leave you with in a minute, is the fact that rocks in Indonesia can go up fast and they can go down fast. So you've got very significant, what's called tectonism, very significant movements. Okay, a fold belt. This is a lovely fold belt. On the western side of Sulawesi, you can see the fold belt here, even on the bathymetry. So a whole series of folds which are coming off of the western side of Sulawesi as it is been moving this general direction. I don't think I have time to show you much more on that, but I'll show you what a fold belt looks like. This is what a fold belt looks like on seismic data. So here you have that same West Sulawesi fold belt, and courtesy of ion geophysics, they've given us this seismic line, which shows how, as it gets compressed, it is decolled somewhere down here, somewhere it's formed folds with some faults as well, but mainly just folds. Very interesting fold belt. Unfortunately, there's no oil in this that anybody's found yet. So that was disappointing. We've drilled a few of these, but it's not been very successful. Some fold belts work, some fold belts don't. Most fold belts are quite complicated. Moving down to the south, here's southern arm. This is the southeastern arm here. And off the southeastern arm are some islands. a famous island called Bhutan. Many of you have probably been to Bhutan. And I've also put Lompo Batan in here as well, because I'm still trying to work out what it's doing there. If anybody knows, please let me know. This is Bhutan Island. Bhutan is interesting. It's a fold thrust belt. So there's been movement and it's formed a fold thrust belt. But in dark green here is very good, very rich organic oil source rocks. And this oil has migrated up, mainly up the thrusts and faults, and into overlying beds here, which haven't got any seal, and the oil has reached the surface. And this is what you find. You have asphalt, world-class asphalt deposits in Bhutan. Most of you, I expect, know this. So this is bulldozed out. They probably clean, it's mainly in sandstone, so it's heavy oil, which is bituminous and asphaltic. It's the heavier part of the oil which gets left behind. The light bits all evaporate off. And this is a world-class deposit on Bhutan Island. I mentioned Wallace, Alfred Russel Wallace. I haven't got time to tell you about Arthur Wallace, but anyway, he came out with the famous Wallace Line, which was a faunal divide between Australian things and here. For a while, he lived here in North Sulawesi. He lived all over, but he lived here about 3 months, I think. And he realized that not only the fauna was different, but the rocks, the geology was different. He wasn't really a geologist, but he did understand that he tried to come up with the geological reasons as to why this was different. And we can now see that actually the boundary between Sunderland arguably can run down the western side of Sulawesi. So this western part of Sulawesi is probably best put in Sunderland. So this obviously is a geologic reason for the Wallace Line. Moving to the north, lovely area, North Sulawesi. There's some interesting volcanoes. Sopotan's probably the biggest. Oh no, Klabat I think is the highest. And you've got all the islands to the north, the Sangihe Islands, and then you've got the lovely Malacca Sea before you get to Halmahera. I'm going to show you Dukono because that's interesting. That's misbehaving again. But you've got two trenches, deep water areas, Sangihe Trench and the Halmahera Trench. And you have this line of islands in the middle called the Mayu Talud Ridge, which isn't a spreading ridge. It's some form of tectonic ridge. We perhaps still don't fully understand it. So it's quite interesting. Okay, the geology is volcanics in the north end. Morotai is not volcanic, but lots of ophiolites and old ocean crust, oceanic rocks and deeper rocks on the east, just like in Sulawesi, and a few more volcanics down here, and various limestones and other rocks down here. It's got some similarities to Sulawesi, but it's a much smaller version. What's happened? It's come a long way. It's come a huge distance, probably 1,000 kilometers or more. It's been pushed by the Pacific spreading and the Philippine Sea spreading, and it's come from over here. And it's slid on a number of faults, but particularly the Sorong Fault, which some of you may know. It slid along here, and it's crashed into the northern arm of Sulawesi, and it's subducted this oceanic plate, which is called the Malacca Sea Plate in between. So it's interesting island. And here's Dukono. Dukono is the beast. Any volcano that's near people often gets named. This one got named the beast. It's currently erupting again. As with Indonesian subduction volcanoes, lots of material is coming down the slopes. You're avalanching dust, ashes, blocks, broken bits of lava domes, all tumble down. They come down the streams. You have an Indonesian name called Lahar, which is where you get a river of mud and volcanic material. And you can see that's the damage. It causes lots of trouble. This is a map of the Malacca Sea. And we know there is what's called a Malacca plate, oceanic material. There's only a little bit of it left in the middle. Most of it's subducted to the west, a bit of it's subducted underneath Tucono. And this is almost unique in the world. We don't know of another example where two volcanic arcs are coming together and are eventually going to hit each other. This is going to disappear because this is disappearing this way and this is disappearing this way until eventually the Malacca Sea is going to disappear. I'm not sure I'll see that happen. Moving to East Nusa Tenggara. Okay, the beautiful island of Flores is here. South of it is the Savu Sea. This is quite a complicated area, but that's typical of Indonesia. The volcanoes run along here. Here's good old Tambora, which 1815 is often referred to as the biggest eruption in recorded history. This whole sea area was covered in pumice. Ships couldn't even sail through it because there was so much pumice floating in the sea at the time. Caused utter devastation to this part of Sumbawa. There's a number of, many of you know Komodo Islands. This is a whole series of volcanoes along Flores. There's a lovely caldera we went to the other day, Sengang, as here. And Lower Toby's in the news. Lower Toby has shut down most of the eastern side of Flores. Everywhere here is shut down thanks to Lower Toby. Other islands, Alor, Wetor, you can see there's a big fault running down here. That's not difficult to see. Here's the Timor Trough, and lots of other things, but not time to tell you about them. This is interesting. This is worth going to see. In the middle of Western Flores is some limestones here with caves in, and there's a cave called Liang Bua. Since the 50s, they've been finding bits of bones, but in 2003, they found a near complete skeleton. You can go and see this. It's a lovely valley, beautiful for farming, beautiful for hunting. I can see exactly why they lived there. They lived there during the last ice age. The last ice age was typically this sort of time frame, the last up till 13 years ago. So these people were living in this cave, certainly burying their dead in this cave, because this was a nice place to live in the Ice Age. You wouldn't want to live in Europe in the Ice Age. You would want to live here. And Flores man, for some reason, we don't know why, was only about 100 centimeters tall and only about 30 kg, and obviously called the Hobbit. Interestingly, there are still pygmy humans on Flores, but apparently they're not related. There's some other reason why they're small. There's different reasons why people go small, so we can't be certain, but this is well worth a visit, beautiful. You have to go to Ruteng here and then drive north from Ruteng. I promised you the Flores and Wetar back arc. Here's the subduction zone underneath Java. This is movement, and shown here in red. Where the Australian plate hits Timor, the subduction ceases. So there's very little subduction underneath Timor. Instead, the movement flips to a back thrust along Flores and Wetar. And this is very dangerous. I advise you not to live in northern Flores, or this is what happened to northern Flores in 1992. Huge tsunamis. Not surprisingly, this is a seismic line here through the Flores thrust. Here's what happens. The thrust moves, and it moves a huge amount of seabed up with it. And therefore, this creates has the potential to create huge tsunamis on this northern side of Flores and Wetar. Not a good place to live. But of course, many people have to because it's great fishing and it's probably a lovely place to live. Better to live in Liang Bua if you can. Okay, Lower Toby. What a problem this is. Okay, here's a satellite image. Lower Toby has two parts to it. It has a male part here, Laki, to the northeast, and a much bigger female part, which is the problem. The female bit's the problem. This is the this is the one that's causing trouble at the moment. This has been erupting all year, putting clouds into, and now no airlines will go anywhere near this. They used to fly around these things, but now they won't go within about 500 kilometers of these. So now this causes havoc to aviation. So you can't fly into anywhere in Eastern Flores all of this year. You can see here what happens, how much material comes down and goes down into there's lahars, there's avalanches, there's all sorts coming down off here, off of Tuampuan. Nearly finished. Banda Arc. This is fascinating. This is the Banda Arc. Many of you, I expect, have been to Banda, but there's this area called Weber Deep. Very interesting. The Weber Deep, he was another German, and he named it on some trip. Here, German biologist, he wasn't a geologist. The Weber Deep is formed as it's an exposed fault plane, probably the biggest exposed fault plane in the world. This part of Aru and the islands here has slipped aside, exposing the deeper rocks underneath. It's called the Banda detachment. So it's a very, very low angle fault. You can probably see as this is bending round probably against its better judgment, and it's caused this big slip here. This is an exposed fault plane on the seabed. So you can actually see the striations of the fault on the seabed running this way as it's opened and slid away. Quite interesting to be able to see that. Okay, I wasn't sure about showing. This is Timor Island itself, is a mountain range in the process of being built. Hasn't finished building yet. It's still, this is Australia hitting with Indonesia, and it's being uplifted. So this area, the subduction is largely finished, and this part of Australia is hitting into Timor and causing serious folding and thrusting. And that's why at the back you've got this wetar back thrust. But eventually it's probably going to get bigger and bigger and bigger. It's how you form a mountain range. Okay, moving on, one of my favorite parts is Irian Jaya, or what used to be called Netherlands, New Guinea. Then it was called Indonesian New Guinea. Then it was called Irian Jaya. And for some reason, they've changed it to Papua, which is this bit, and West Papua is this bit. So it's easier to say Irian Jaya rather than have to say West Papua and Papua all the time. So the mountains, this is the highest range in Indonesia. Puncak Jaya is nearly 5 kilometers high. I don't know much about it. I've never been there. I do know the Lengguru fold belt. There's an interesting look at this. You can see the folds sticking out. This is a fold belt, completely different terrain to the rest of West Papua. Kamam Highlands, I know reasonably well. They're an old piece of Paleozoic. Above it is a Sorong Fault. Here, if you've ever been to Raja Ampat, you'll have gone to Waigeo, probably. The ferry runs from Sorong to Waigeo, and then you can go out onto all the lovely islands and go diving and do whatever. Okay, I could go on. I'm going to show you Bintuni Basin quickly, and I'm going to finish with the Cyclops Mountains. Okay, geology. Right. Old rocks, you can see, like Paleozoic basement here, some very old rocks in the highland area. But in green is what I'll show you in a minute. In green is ophiolite. That's oceanic lithosphere. So all along here is oceanic lithosphere, and you'll see why it's oceanic lithosphere in a minute. After I get rid of Bintuni Basin is a hidden Jurassic basin. It's a basin where Shell used to have their operational headquarters here when they were running Netherlands New Guinea Oil Company, or Matshafti, or whatever it was called. And they explored from here all around, but all they had was gravity data, and they couldn't work out what was in the subsurface. Now we can see there's a hidden Jurassic basin under here, and there's huge volumes of gas in Bintuni Bay. Many of you know of the Tangguh LNG project, which is based exactly here, about where that dot on the eye is. very interesting area. Chandrawassi Bay is partly oceanic. It's been spreading, it's been moving. Bintuni Bay, perhaps no surprise, but I know underneath there's a whole series of east-west faults, and that has caused collapse and allowing the Bintuni Bay to come into this, almost broken through to Chandrawassi Bay. This is called the Bird's Head proper, or the Doberai Peninsula. This is the Bomberai Peninsula. And this is, Onin Ridge is an inversion. This isn't, but the Onin Ridge is an inversion. So very interesting. I could go on, but there's just to give you a flavor of West Papua. And I'm going to finish with the Cyclops Mountains. This is Jayapura. Many of you may know Jayapura is here, Jayapura. And right next to Jayapura are the Cyclops Mountains. What are they? They're a piece of ocean which has been thrust up. Lake Sentani used to be open to the ocean not that long ago, probably a few tens of thousands of years ago. It's now an inland freshwater lake. But we now know that there's such a thing called abduction. You get pieces of oceanic plate which can get thrust up, particularly along strike-slip faults. So you're getting compressional strike-slip faults which push up a piece of seabed. Now, this has obviously come up some distance. I don't know exactly how much, probably a few kilometers. It's been thrust up against they could only call this the Range A. They seem to be lacking in inventiveness around here. Range A is here, and this is Cyclops Mountains have come up against it. This is what an ophiolite looks like. I've seen a number of these. There's some spectacular examples around the world. You have sediment on the top, you have pillow lavas beneath, you have vertical dikes. This is what causes seafloor spreading. These inject in the middle at the mid ridges, and they spread in either way. So this is a sheeted dike complex, beneath which you get gabbro, which is basically it's a basic rock, and then you get all sorts of other rocks, mantle rocks, such as types of peridotite. This is where your diamonds come from down here. But this is a piece of oceanic lithosphere which gets thrust up onto the places like the Cyclops Mountains. Absolutely fascinating. Okay, I've finished just about. What have we learned? We've learned that there's fast plate movements, and you can see that I convert to 1 million years. So I work in millions of years. So 50 kilometers is the type of distance that the plate can travel in 1 million years. But vertical rates are much, much slower. They're about a 50th of that. You can go up and down 1 kilometer in 1 million years. Many geologists will tell you that's impossible. But if you now look in Indonesia, you can see it's very possible. We can see many examples of hills going up in 1 kilometer in 1 million years and basins or sea areas going down 1 kilometer in 1 million years. So we know this is real. And Indonesia should be teaching the world geology, not the other way around. Okay. Some of it, though, is episodic. We've been looking at this. So about 10 times in the last 40 million years have been periods where it's even more rapid. So there's periods where it's just going along normally, but there's other periods where it's very fast. And it means that if you try to understand eustatic sea level changes, where the sea level goes up because of volume changes in the world or ice sheets or something, which go up and down maybe 100 or meters or so, not only is the rate similar, but obviously the order of magnitude is much greater. You rarely go more than 100 meters up and down, but you can go up or down 1 or 2 kilometers. So much, much more than eustatic changes. And Peter Lunt and I described this recently, and we can now show a number of unconformities. Unconformities in the main represent tectonic activity. If you're faulting and folding the beds, you're going to form an unconformity somewhere. So we can see lots of unconformities even through these limestones. This is going from West Sumatra to Sulawesi, and you'll see there's actually more limestones as you go east. Indonesia is a huge repository of limestone. There's vast volumes. There's probably more CO2 in the world locked up here than almost anywhere else. Huge quantities of limestone. And what it also shows you, it doesn't matter what the sea level does, the reefs keep up, whether you drown them or whether you rise them up. Reefs are incredibly resilient. It doesn't matter what the sea level does, the reef still persists. So don't worry about your reefs, okay? I think that's it. So I'd like to thank Peter Lunt, who I often work with, Herman Darman, who has been very helpful, and Steve Bergman, who's a diamond expert, and of course my wife Pooja for help and support, particularly in field work, and Mike for prompting me to do this, because otherwise I wouldn't have done it. And inspiration from Mr. Van Gorsel and Charles, who I used to know very well, unfortunately has passed on. He's a very nice guy. So really, that's it.
Wow. Peter, that was amazing. I don't know how you managed to get through all of that, and you're on slide 507. Well, we actually, Peter told me he didn't want any questions, so he's filled all of his time, which very, very expertly. But maybe students are here, aren't you? Students, where are you, students? Any student like to ask Peter a question, because you should have a few questions from that. Yes. Can we?
All right. First of all, I want to say thank you for your presentation tonight. Okay. So as you have presented, Indonesia has a lot of volcanoes, a lot of tectonic plates that results in many volcanic eruptions and many earthquakes. Now, as you've mentioned in one of the slides, Indonesia recently found a uranium deposit in Bangka, right? So
I wouldn't say a uranium deposit. They can find uranium in the sediment.
I see.
Okay. I don't know what quantity, but probably very little, but maybe enough to process. Okay. So there's definitely uranium around. I suspect that there's vast areas of Indonesia that haven't been studied properly, and there may be other areas of higher concentrations of uranium, but Bangka is an example where there's definitely some uranium.
Okay, a hot place then. Okay. So recently, there's been a lot of talks in shifting the worldwide industry from fossil fuels to renewable energies. Now, one of these renewable energies are obviously nuclear power. So,
well, the renewable crowd wouldn't include nuclear in renewables. It doesn't matter. You can call it renewable if you like. It's using uranium, but yeah. Okay.
Now, the Indonesian government and Southeast Asia in general is very not open to these nuclear facilities that can be potentially used to harvest a lot of energies. Now, partially, this is because of Indonesia's own geology system. We have a lot of volcanoes, we have a lot of earthquakes, so it is very unsustainable for us to use nuclear powered facilities now.
Right, but you have very little in renewables. I'm pleased to say you have very little wind, except perhaps South Sulawesi. You have very little area that you can really honestly use for solar farms. You've got geothermal, but that probably reaches its limit. I'll follow geothermal and try and give an update at some stage. But I mean, in essence, if you keep putting cold water down into rocks, you're going to cool them down. So I'm not sure how successful geothermal really is. They've tried to sell a lot more recently, but failed. So geothermal exists and certainly should be used. Nuclear is the way to go. I'd have a nuclear power plant in my back garden if I could have one. I mean, you have them in submarines, you have small plants. Nuclear power stations now have reached a level where people shouldn't be afraid of them, and it's the obvious way to go. But fossil fuels not given up yet. Let me tell you, fossil fuels have got a long way to go yet. Of course, Indonesia, I'm pleased to tell you, has a policy to increase its oil and gas production over the coming years. Okay, it has a clear government policy to increase oil and gas production. And I think that's absolutely right. The only problem holding back is that Indonesia, for many people, is a very difficult place to do business for all sorts of reasons. But if that were cleared up and made easier, Indonesia could easily increase its oil and gas production. And that's what it's aiming to do. If you want to give cheap, reliable electricity to people in remote parts of Indonesia, which is, I think, a very good government policy, you've got to have use of fossil fuels. Of course, I didn't tell you, but obviously that Indonesia has lots of coal. I didn't have time to show you where all the coal was. It's not on Java. No, I should have done. So yes, there's a lot of coal, and Indonesian coal has been used a lot over the years, and I'm sure it will still continue to be used.
I see.
I'm not going to say what I think of coal power stations, but that's another issue. Give me a nuclear power station in my backyard any day over a coal power one. But nuclear is the way to go.
Okay. Given the chance that Indonesia becomes open to nuclear power plants and they start building these power plants as a substitute to the current fossil fuel power system, what are some precautions that we should have before making them, in your opinion?
Just make sure you've got the best in-class, latest nuclear power plant. And if you have to store any fuel, it's not vast amounts, just make sure you store it somewhere sensibly. I don't think it's difficult. It's well-known, obvious technology. There's nothing complicated about it. All you're doing is heating up water and passing it into a turbine. It's very, very simple technology. You've just got to have the right safety in there. I don't know whether Bangka is the best place to put your first nuclear power plant. I don't have a view on that. But if they can actually use some of the uranium on Bangka for the power plant, then maybe it's a good place. But it was announced a few days ago. Yeah, it's been announced that the government of Indonesia is going ahead with nuclear power plants, quite rightly. Okay,
Lovely. Okay, thank you.
Thank you. Yeah, one or two more questions.
Hi, good evening. I'm Robbie. How are you, Peter? Just one quick question. Maybe it's not from your
geologic.
perspective. Yeah, it's not geologic. Well, of course it's geologic, but most of all, over here, civil engineer knows about earthquake and also knows that the earthquake in Indonesia, where to put it, and etc. But from your opinions, where do we can live safely without any tectonics that have been surrounding by us in Indonesia?
I thought I showed you on the slide. Do you remember the anywhere in the core of Sunderland is perfectly okay. It's almost tectonically inactive. So on the east, Bangka's a good place because it's in the middle of Sunderland. Western side of Borneo, Kalimantan is probably a good place. So there's several places you'd want to go in Sunderland. You wouldn't want to go onto, you wouldn't want to go into Sulawesi or Halmahera. Oh, yeah. But certainly anywhere on the core of Sunderland will be perfectly okay. Okay. All right. No more seismic risk there than anywhere else. I personally think Jakarta's okay, but there are various, you may have seen, there's some insurance risk associated with earthquakes in Jakarta. I'm not sure it's entirely warranted. Most of the earthquakes here are 300 kilometers down. And I'm not going to worry about an earthquake 300 kilometers down. You want to worry about an earthquake that's 10 kilometers, 3 or 10 kilometers down. Those are the earthquakes to worry about. It's not so much the magnitude, it's whether you're standing next to it or not that counts. If it's 300 kilometers under the ground, you hardly feel it.
Cheers.
Oh, right. Right. Okay. Yeah, I can read it out. Yeah, it says from Elok Widyati. It says, is it possible there'll be a shift or change in the area classification because of a natural disaster? Seems like Rembang Madura area, presumably. Yes, I think you may be right. I suspect that I've not really given. I often go to Lamongan Shore Base, and not often, but a few times, and Surabaya. I don't actually worry, but I can see now around that East Java North Coast, you might be concerned. I mean, you have to live with earthquakes, you have to live with volcanoes. It's just a case of, very simply, if you live in an earthquake-prone area, make sure the horizontal beams are connected to your vertical walls. You have to make sure everything's connected, which is why, of course, in a big office, it's just fun being in an earthquake. It's not a danger. But if you have a house where it moves slightly and the roof falls on you, that's what's going to kill you. So if you live in an earthquake area, the Indonesian government probably needs to have better earthquake policies in terms of building codes, like they do in Japan. So it's not my area of expertise, but if I was going to live in an earthquake-prone area, I'd certainly make sure my house was built properly. But it's easy to say, isn't it? I mean, it costs money to build a house to be earthquake resistant. So, many people just simply take their chance.
There's one more, actually very good, the final question here.
Yep.
Which is about whether or not there's a chance of a mega thrust earthquake in West Java. That's a good question, I think.
Right. Yes. So that's the Bibaris fault, which allegedly runs somewhere just south of Jakarta, which has been in the news recently. I think the risk is overdone. I can't really see the fault, and I'm not sure it's any one single fault. It's not the same as the Flores. It might be an extension of the Flores wet-R thrust, back thrust, but it isn't really, because we've still got lots of subduction underneath Java. So we don't have back thrusts because of the blocking of the subduction. There's obviously, it's been posed as a risk that there could be a mega thrust somewhere to the south of Jakarta called the Bibaris fault. The only recorded fault earthquake I can see is about 300 years ago from that, and even if it was that. So I'm not worried. I wouldn't be worried about Jakarta too much. Famous last words, I hope. I'm not.
But on your famous last word, Peter, I think we will bring this to an end. I would like again to thank you for preparing an incredible presentation with a wealth of information in it. And for those of you perhaps who are not so familiar with geology, I think you will have seen tonight that there's so much to know and understand that is forming this country we live in. And I think that was wonderful. I mean, hopefully we can provide a PDF of your presentation to the, yes, so you will get a PDF copy of this. And I think you'll find it a fascinating reference, and I'm sure you'll look over those slides and remind yourself, especially the bit that I missed when you were mentioning water from 120 kilometers. I had to pop out. I'm sorry about that. I did, yes, 120 kilometers, yeah. Anyhow, so, no, it wasn't. Right, so I'll bring this event to an end. Again, one more big thank you, Peter. That was fantastic. Thank you all for attending. And I believe that the curry is being served. So if you would like to go and help yourselves, you're most welcome. Any other questions? I'm sure Peter will be very happy to discuss things with you during the rest of this evening. So I'll bring the formal proceedings to an end. I think, Rifa, are you going to say anything? For the online, do you want to say something then? Okay.
Okay. Once again, thank you, Dr. Peter Woodroof, for the excellent presentation, and also to Pak Mike Dobit for guiding the session. Next, ladies and gentlemen, we have now reached the end of the event. Once again, thank you for your participation, both on-site attendees and also online attendees. We hope we can see you at the next event next year. At last, good evening and stay healthy, everyone. Thank you. For the on-site participants, if you haven't do the re-registrations, please come to this side of the room and just sign the paper from Mbak Wira. Thank you.